Morning, everybody. Um, okay, so what I would like to tell you about today is about the quantum state of the black hole. The, this device needs to get used. I need to get used to this device. The first point that I would like to emphasize is the difference between a quantum state and a geometry. Many of us who work in gravity research are used to think about the gravitational states as geometries. But when you need to think about the quantum properties of gravitational states, then this you have to realize that the geometry is just a classical approximation that sometimes works and sometimes doesn't. And what I would like to tell you about today is about the quantum state of the black hole. And the way I will present the story is I will first describe the outside view, which is the view that is accessible to outside observer, and I will use the relationship between the outside and the inside to try and propose a model for how the interior of the black hole looks like. Okay, so this is what I will do. The sort of the message is that outside the black hole, that we already know, the gravitational state is well described by mean field approximation. In fact, classical geometry is almost perfect, a perfect description. But the radiation that the black hole emits is in fact in a highly quantum state. That would be an important message. And this means that the inside has to be in a highly quantum state. So the inside of the black hole cannot be described by a mean field description. This is the main message. This is, I think, a general conclusion that is not specific to the models that I will present. And then I will try to, so of course, trying to describe a state that doesn't have a mean field approximation is something that is quite hard. We usually don't know how to do that. But I will try anyhow. Okay. So as the late Jacob Bekenstein, who just passed away, emphasize in a paper that I actually don't agree with the actual claims or statements in the paper. I don't agree with, but with this one, with this statement, with this idea, is actually what I will try to explain. So what it says here is that a black hole, this is true in general for gravitational states, but I'm focusing on a black hole. A black hole must be subject to quantum laws. So it's not it's special, but you will see how. But it's not special in the sense that it is exempt from the standard laws of physics. That's the main idea. And that was the original idea that led Bekenstein in all this group around Wheeler, but especially Bekenstein, to think about the black hole entropy and so on. And as time passed, when Hawking did his calculation, we moved as a community to doing quantum fields in the background of the black hole and sort of neglected to understand the properties of the actual state. And I would like to describe that as well. So the other thing that you may have been aware of is the conundrum about the information paradox and so on. I will not say too much about it. I think Laros and maybe you will also say more about that. But I think most researchers in the field have reached the conclusion one way or another that unitarity is actually holds in this type of evolution. And so from this point of view, as this running circle shows, is that the shift of emphasis is from understanding whether the evolution operator is unitary or not. If we understand that it is unitary, then what we need to understand is the properties of the state. And once we understand the properties of the state, we will be able to calculate and say things about the many processes that involve black holes. Okay, so let me start explaining this idea of the difference between the quantum state and a geometry. So now, in general, what we would like to do is calculate expectation values of matter operators in the state that is a state of matter. The M stands for matter, and gravity. Here, the gravitational state is the black hole. This is what we would like to calculate. But usually what we do is we calculate essentially in quantum fields in Kerr space-time or effective field theory in a fixed background. This is, since we are in a Born Symposium, this is, I found a way of introducing also Born, and this is actually the Born-Oppenheimer approximation, right? So, for example, if you calculate a scattering amplitude from a heavy nucleus, what you do is you replace the field, the state of the nucleus, you replace by its Coulomb field, and this is plugged as a function into the wave function of the electrons, the scattered electrons. This is an approximation. Good. This is an approximation. And let me explain to you what are the corrections to this approximation. This is what we need to understand when we would like to, when we want to go beyond the Born-Oppenheimer approximation. So in this case, right, this is what the classical limit. And now, what is the parameter that defines the difference between the true quantum expectation value and the Born-Oppenheimer approximation? This is the usual parameter. It's the dimensionless h bar. You take the Compton wavelengths of the objects that you are interested in. You take the geometric scale of that object, and the ratio of these two is the dimensionless h bar. And in the case of the black hole, it's just 1 over the black hole entropy. And this parameter is in Gia's, in Cesar's discussion is called 1 over n. In ADS-CFT is 1 over n squared, and probably it's also 1 over your n. Okay, so I should add, I wasn't sure, and then, right? And so, yes, and then the classical limit is the limit when this parameter, this expansion parameter, goes to 0. And now let's look at the corrections, okay? So the corrections are, as usual, they're an expansion, the perturbative expansion in h bar, in the dimensionless h bar. And typically, they start with the first order and then second order and so on, unless there is some symmetry that says that one of the coefficients vanishes. And in the black hole case, in the cases that I'm interested in, they are known. Now, from the effective field theory point of view, these are huge non-perturbative corrections, because from that point of view, the corrections to the classical expectation values are exponentially suppressed, e to the minus SBH. Okay? So you don't see these corrections when you do effective field theory. And they are key to what I will discuss later on. So the classical limit in this case is dimensionless h bar equals 0, 1 over SPH equals 0, and in terms of the black hole parameter, is G Newton goes to 0 and black hole goes to infinity, keeping the Schwarzschild radius fixed, okay? And in this case, you have to remember, this I will not discuss in further on, but the true expansion parameter, when you calculate properties associated with black hole decay and so on, is not 1 over SBH, but is n, the number of emitted particles, divided by SBH. And that number becomes order 1 at the page time, at the midpoint of the black hole evaporation. And that's why many of the arguments cease to be, the perturbative estimate cease to be correct when the number of emitted particles becomes comparable to the entropy of the black hole. Okay? So these are general discussions. Now Hawking set, as I will show you, set all these corrections to 0. And I will show you what if you set it to exactly to 0, what is the conclusion that you reach. Okay, so now I would like, as I said initially, I would like to find out what is the state of the black hole. And the way that I would like to answer that question is to look at the emitted radiation. If the black hole starts from a pure state, the density matrix of the state of the emitted radiation is the same in the sense that the eigenvalues are the same. The non-zero eigenvalues are the same. And for those of you who are skeptical whether black holes can be in the pure state, there's a little calculation here that shows that the actually astrophysical black hole, say solar mass black hole, are the purest objects that you can ever imagine. Because of this, let me not go into it because of the time. So let me remind you, this is something that I will need for the continuation. Let me remind you of the way Hawking calculated a black hole radiance. What he did, he considered a collapsing shell, and then he calculated the state of the emitted radiation, the density matrix of the initial vacuum in the basis of the outgoing operators. And in this case, once you know that density matrix, actually in the paper itself, he calculated only the two-point function and said things about the full density matrix, but I will show you how these two are connected. And for example, you can, in this case, once you know the out density matrix, okay. Once you know the out density matrix, yes. Once you know the out density matrix, then you can calculate anything that you would like. So I think the lights just went out. It's not a problem of communication, right? Hmm? Well, yesterday also the screen went up. So it's different. Okay, let me, while they are setting up the let me tell you in words what Hawking found, and then I will explain once the slides come up again. I'll show you in formula. So what Hawking did is he calculated the single particle density matrix, okay? Initially, he calculated essentially the two-point function, And what he found was that the two-point function was a diagonal in frequency, right? In this case, the label of the modes is only their energy. It's a Schwarzschild black hole. It's their energy. And he found that the two-point function was a diagonal in frequencies, and that the multi-particle density matrix elements, so density matrix elements with different number of particles, is exponentially suppressed. And so what this allowed him to conclude that the full density matrix of the emitted radiation is diagonal. And if the full density matrix is diagonal, this means that the state of the emitted radiation is mixed. And then he concluded that since the initial state, the vacuum state, is a pure state, and he ended up, after the black hole has evaporated, with a mixed state, this means that evolution is not unitary, and that's what he called. So this is described here, what I said in words, right? So in this case, this is the two-point function. Its elements are given in terms of the Bogoliubov coefficient between the ingoing modes and the outgoing modes. And this is what I told you. This is an important point because I think this is a property of any model that approximate the Hawking model and takes into account the fact that there is a horizon separating the inside and out. This means, in this case, that the off-diagonal correction in mode occupation number to the density matrix are suppressed. And technically, the way it comes is that to get these off-diagonal elements in particle number, you need these, you see that the off-diagonal elements are proportional to, unlike the diagonal, which is proportional to beta beta bar, they are proportional to powers, uneven powers of bars and non-bar Bogoliubov coefficient, and they, in the Hawking model, they are proportional to a delta function of omega plus omega prime. Omegas are frequencies, they are positive, and therefore, if you actually look at it, they are exponentially suppressed. And so this is a property of the density matrix of the emitted radiation of the black hole. And the two-point function, in this case, is, I'm talking about free fields, which is essentially all that I need. In this case, the two-point function fixes the full density matrix, and the density matrix is given as an exponential of a quadratic form. Quadratic form is this one here, and therefore, in this case, we know from the two-point function the full density matrix to the approximation that we needed. Okay? And then you see what Hawking found is that the two-point function, as I said, is diagonal in frequencies, and therefore, because the off-diagonal elements in particle number are suppressed, this means that the full density matrix is diagonal, and as I said, this is the origin of his correct claim under the assumptions that he made, that the evolution of a black hole is non-unitary. Now, so how do I include these H-bar corrections that I was telling you initially? The way that we did it here, but I think it's more general. Let me describe it anyhow to show you that there is a calculation that we actually did to figure out how these H-bar corrections, the dimensionless H-bar corrections, so taking into account the fact that the black hole is an actual quantum state, how they come about. So in this case, we took the original Hawking setup, where you had a collapsing shell. In this way, the particle production was calculated. We took that collapsing shell and assigned a Gaussian wave function to it with width that corresponds to the expected width of the black hole, so 1 over SPH in dimensionless units. And it's actually a non-trivial technical problem, so that's the original Hawking calculation. And what we now do is, as I said, allow the black hole state to become quantum, to fluctuate quantum mechanically. And the technical way that we implement that is by allowing the shell, the collapsing shell, to fluctuate quantum mechanically. And so in this case, the way that we do the calculation is that the original Hawking calculation is done. There is an integral over the time that passes from the time that the shell starts to collapse until it reaches its own horizon. That's the V0, and then that V0 actually fluctuates. And I don't need you to follow the details. This is just to show you that there is an actual calculation behind the words. And this is the result, but essentially what the result says in this case is that when you include quantum fluctuations of the shell, the two-point function gets a small, uniform, off-diagonal correction, which is essentially of order square root of h bar, which is exactly the kind of strength that you need in off-diagonal terms to get corrections to physical observables that go in powers of h bar, and not of square root of h bar, because the off-diagonal terms only appear quadratically in observables. That's why I said it doesn't matter. It's really the width, the dimensional width. Yes. So the fact that it's a Gaussian is unimportant. It's just the fact that this V0 fluctuates. It's like, in this case, it's like if you pass a light through an infinitely thin surface, then it will not disperse. And here, because the surface is fluctuating, you get small dispersion and essentially uniform, because the scale of the fluctuations of the surface is much, much smaller than the scale of the incident wavelengths. And so that's why I said there is a calculation, but I think the results are more general. And so it's uniform. In the diagonal, you can ignore, because they are on the diagonal. They are large entries that are the Hawking entries anyhow. So it's there are large entries on the diagonal, order 1, and then all the others are off diagonal, and they are all limited to the thermal window. So they are emitted with frequencies that are essentially the Hawking temperature, but instead of being diagonal, they are small off-diagonal corrections. And in this case, we did it for a scalar field, but that is not, yes. It could be, I mean, the composition of the shell here is unimportant, because we still keep, because of the high redshift, the geometric approximation is still valid, except that instead of having a sort of non-dispersive lens, you have a dispersive lens. And the composition of matter, Hawking on this was right. The composition of matter is not very, very important. I think you should get similar results. Okay, so you will tell me about it. Okay, so this is what I was saying before. And then the point is that I'm missing a slide for some reason. Okay, it's the previous one. So you remember my discussion about the multiparticle elements being suppressed, off-diagonal elements in multiparticle space. This was this one. This is still valid because we still have a high redshift. We still have something that looks like a delta function in the off-diagonal matrix element. And so in this case, the full density matrix is determined by the two-point function, except that the two-point function is different. Okay, so now I'm coming to the point of arguing that the emitted radiation is in a highly quantum state. Now, many of you, I'm sure, so when they tell you that black holes radiate like black body, you have a mental picture in mind that if you had a black hole with the temperature of the sun, it would emit radiation that is similar to the radiation of the sun. But this is incorrect. And the way that you see it is you have to go to the correct basis of the wave, the wave packet, right? The black hole emits, the Schwarzschild black hole emits particles into essentially flat space. So you have to go to this basis. And then you can calculate essentially the total number of modes whose occupation number is substantial. This is implicit in Hawking's calculations, in other calculations, but I haven't seen it done explicitly in the literature, so we did it. And this is the answer for the total number of modes. Now, the number of particles that are emitted during this time is also is given by n by gamma, so the rate times delta t is T Hawking. And therefore, delta t is the total time that you observe the emission. Right? The black hole evaporates, you collect the radiation, and you ask how many particles were emitted during a specific time to what number of modes. I don't have I didn't do the detailed calculation here, but this we discuss in that paper that I mentioned. No, in this case it's the observation time. The rate is determined. So the ratio is actually 1. That's the whole point. So what happens is that the black hole emits one particle every Schwarzschild radius. Right? Unlike the sun, that emits photons, let's say at green or yellow, mostly at yellow, and its size is much bigger than that. So you have many, many photons, many yellow or green photons, and the radiation field that is emitted is then semi-classical, because occupation numbers are large. But a black hole it's really a quantum emitter. So it emits a single particle every light crossing time. And therefore the state that you get has small occupation numbers. Okay? That's an important point. This you can see from the original Hawking calculation, but in this case, the state was mixed, so there was no point in saying that it's a highly quantum state. But if you are thinking about a unitary process of emission, you have to accept the fact that the state is highly quantum. Again, I think we see it in our model, but I think it's a more general property of any model that... Okay, so to summarize this, let me show you how the different models work. So Hawking model is essentially diagonal. This estimates say that the density matrix of the emitted radiation is diagonal. In our case, the semi-classical model, we get corrections to the two-point function, but the structure remains here. And for those of you who are familiar with the Page model, there he separates the inside and the out without taking into account the fact that there is a horizon, and therefore he gets essentially uniform distribution of small eigenvalues on the full density matrix. Okay. And as you say, this is what I said before, state is highly quantum. Okay, let me now go to the last part of the talk, which is what can we conclude from what we learned so far about the state of the interior. Okay? So now, in general, there are three possibilities. So you have to think about the interior as some state. The matter that created it fell through the horizon, and now we have to understand how this excited state is distributed. So classical GR suggests that the state is, the matter is concentrated near the origin in a highly excited state. That we can dismiss immediately because it is, it's a remnant so in this guy, so it conflicts with many other issues. Let me not get into that. And the other point which you may not be aware of is that imagine that you do have a highly excited state with strong gravitational field near the origin, it would be completely unstable to particle production. And so this sometimes is not always known, but if you think about it, you see that it cannot be stable if it satisfies normal quantum rules. So let's dismiss that. The other possibility is that the matter is concentrated near the horizon, in the proximity of the horizon, in a highly excited state. This is essentially the idea of a firewall. I will not discuss that. I think Laros and you will discuss it later. And what I would like to concentrate is a model where the state is more or less uniformly distributed throughout the interior. Okay, so what do we know about this thing? First of all, we said if we start from a black hole which is nearly in a pure state, then the emitted radiation is the purifier of the interior. So this means that the interior has to be in a highly quantum state. The first conclusion is that it cannot be described by mean field. This is what it means, a highly quantum state, that the quantum fluctuations are large, and so the mean field description is not valid. This means that we cannot assign a semi-classical metric to the interior. That has been this idea that we need to do that has been an obstacle in many of the discussions. So my conclusion is that it is not possible. So what the picture is that you have a highly semi-classical interior, a transition region that is fluctuating but not a highly fluctuating region, that's the horizon. And then inside you have an interior And we actually estimated the size of this. But let me go on and explain the idea. So, right now, the other thing that we know is that the black hole has to be a highly excited state. And if we make a simple estimate of the density of states that is needed, we find that it's higher than the ones that we encounter for normal quantum field theories. So most likely, it is not possible to describe it even without mean field description with normal quantum field theory. Okay. Now, so let me try now to propose a model in a more detailed model. And it actually turns out that the scaling relations are similar to the ones in Valley and Gomez. So the view of the black hole is a gravitationally bound state. It has roughly SBH relativistic modes. The energy of each mode is 1 over Rs, so they can fit inside the black hole. The difference between the previous discussions is that, again, we do not have a mean field description. If you look, this means that the energy bounds are saturated inside the horizon in the interior. As I said in answering George's question, the horizon is transition region between the semi-classical domain and the highly quantum state. And you can see, I don't think I will have time, but you can see that particles are produced only near the horizon where the field, gravitational field is largest. So they fit the particle production picture of Hawking. And falling objects actually don't survive the fall, but it doesn't happen at the horizon. It happens parametrically at parametrically large distances from the horizon. And let me no, it's actually the parameter that always appears is square root of SBH. So it's LP over RS. So it's much larger. It's much larger than LP, and it's much smaller than RS. That's this I didn't know. Yes, it's almost near the horizon for a solar mass black hole with this expectation is about a Fermi away. So it's not, but it's still a macroscopically large distance, right? This depends on the strength of the fluctuations. This is determined by the H bar, essentially. All of that is determined by that. I can explain, but okay. So now, for those of you who like Penrose diagrams, here are some Penrose diagrams, but a word of caution in this context, Penrose diagram doesn't really capture the essence, the physical essence, because the actual Penrose diagram for quantum fluctuating horizon is that of a Minkowski space, because you never know if something is inside or outside. So a Penrose diagram is good for describing the causal structure of classical states, but is not a good idea to describe that. Let me do that anyhow, because people are used to thinking about it. And so this is the classically motivated, essentially based on the analytic continuation, right? There's no other reason for that. The firewall proposal looks like that, so there is a highly excited state near the horizon. Fuzzball, the description is sometimes fuzzy, and there's some, there isn't a complete agreement among the different groups working on fuzzball what the description is. This is Matour's version, and this is the quantum state that I was describing. So the interior, the whole interior is essentially quantum, and what Marika Taylor and Kostas Kendris argue is, I believe, something similar. At least that's what they told me. Okay? Okay. Now, so let me be a little bit more specific after I describe the general properties of this state. Since the chairman is very quiet and relaxed, I will continue until he will stop me. No, but we had a little break, so I think I. Okay. But I didn't see what you showed me. So, again, I can stop anytime, so tell me when and I will. Oh, very good. We have too much time. I thought you were saying minus 10 minutes. Okay. Very good. Okay, so let me explain in the remaining minutes that I have. Let me show you how this general concept that I was describing look in a more quantitative estimate. Okay, so n is equal to SBH, is Rs square over LP square. I ignore numerical factors here. The energy is MBH, is n over Rs, is Rs over LP square. And the entropy is LP square E square. Okay? So again, it's a special relation. Usually we don't get S goes like E square. So now, let me try to see how the density of states here looks like in the inside. So dn dr d omega is R square over LP square theta of 1 minus R omega. So the modes have to fit inside the horizon. And when I integrate this to get the entropy density and the energy density, I get 1 over R LP square and 1 over R square LP square, which is leads me to see that S is squared over rho. Again, a very unique relationship. And P is equal to rho. That's what I find from the simple quantitative estimates. Now, this equation of state is actually very interesting. Yes? No, this is the total entropy. This one? Don't know. You are worried? Okay. Now, I don't expect you to actually follow the calculation. This is just to show you that we did them. And you can look at the final results, and then if you find a mistake, you let me know. Okay? So, but you see, this equation of state is actually very special. In fact, the only state of matter that I know that actually satisfies that is our strings, highly excited strings. And this fits with the previous expectation, right? Hmm? No. It's spherically symmetric. So spherically symmetric. The equation of state rho equals P. It's not a CFT, first of all. It's just an estimate of the density of state, and I'm assuming here spherical symmetry. Yes. Right. you can think about it as two-dimensional, but they can live in higher dimension, right? I'm not suggesting that this is a state of highly excited string, although it's a very tempting possibility, and we're trying to understand that. All I'm saying is that in normal gas, for example, or normal matter states are not described by this equation of state. And there are additional clues, as I said before, that the density of state that is required in normal situation is much lower than the one that you need. Okay, so this somehow fits. Okay, now you can ask now whether this bound state is stable to particle production. So the first observation is that the emission of particles with wavelengths that is much larger than the size of the bound state of the black hole is suppressed, exponentially suppressed. And the emission of particles with wavelengths that is much smaller than Rs is exponentially suppressed because of this. I have a slide later on. If I have time, I will show it. And if you look at stability against emission to particles which have energy 1 over Rs, the scaling relation continues to hold with one less particle that has energy 1 over Rs. Okay, so it is stable for that emission, and this is similar to what Dvali and Gomez find. Now, as I said, the quantum fluctuation of this state are large, and we can describe that more explicitly by looking at creation operators for these states. And then you find actually that quantum, if you look at this state and you evaluate the variance in higher moments, you find that they are large. This is in contrast to coherent states, where occupation numbers are large and fluctuations are small. So this is really a state that cannot be described by a mean field approximation. Well, you can do it, but the results will not be meaningful. Okay, so the picture is that we have a region of space-time that is highly quantum. It is described possibly by the state that I was trying to describe it. And there is a transition region here, which in the models that we have based on this estimate of the fluctuation, the distance there is essentially a LP, well, it's square root, in dimensionless units, it's square root of Rs over LP. So, so it's parametrically larger than L Planck and parametrically smaller than the Schwarzschild radius. And in this case, I think I still have time for doing a little bit of a calculation. So I said that the particle production is occurring near the horizon, and you can see that by applying Schwinger formula for pair production, for E plus E minus pair production. You replace the electric field by the gravitational field. Here you can get the scaling from the scaling relation that I was presenting before. We find that the gravitational field is E over Rs. We plug it into the pair production formula, and we see that the pair production rate is maximal at 1 over Rs. And in this case, you see explicitly that the rate is exponentially suppressed for regions that are smaller than Rs, and of course, outside the soliton, outside the black hole, the gravitational field decays as a power, and therefore the per production rate decays exponentially. So this picture fits. Okay, if you now calculate the energy density, again, as I said, you cannot use mean field, but you can get an idea of the nature of the state by looking at the average energy and the average fluctuations. And in this case, if you estimate the effective temperature that this state has, it's given by 1 over square root of RSLP. Okay? Instead of 1 over RS square, which is the Hawking temperature, or 1 over LP, which is the Planck temperature, this is a geometric mean. And this is why I said that it's a Fermi, or this sets the size of the transition region. Yes, and now we can also look at what happens to a classical object that falls into this. And we see that the mean free path, again, by looking at gravitational interaction of something that interacts with this state that I was describing, then we see that the mean free path is at most RS for modes that have wavelengths of RS, and for objects that have wavelengths that are much shorter, it's much shorter. The higher the energy, the more the object interacts with these modes, because it interacts gravitationally, and the smaller the mean free path. Okay, so I think let me conclude now, and sort of remind you what we did. I was explaining about the difference between the quantum state and the geometry, and how corrections to expectation values of operators change when you take into account the quantum fluctuations of the geometry. And I was describing the quantum state of the black hole from various perspectives by studying the radiation that it emits, taking into account the quantum corrections. And if you are interested in more details, you can check. There are many papers, mostly with Joey Medved, that we wrote in the last year. Thank you. Square root of 1 over the entropy. Yes.
My question is whether the size of those off-diagonal elements is large enough to explain, let's say, the purity.
Yes, the answer is this is something that I don't discuss here, but we calculated that. And the easiest way to understand that this is true, although you need to look at the actual estimate for the entropy, which we did. We calculated the Rényi entropy of the emitted radiation and showed that it actually goes below the Page curve. And the way to see that this is enough is that you say look at trace rho square, right? This is an estimate of, and then you see that in this case you have n, as the number of particles is growing larger, the entries in this two-point function is growing larger. You have n elements, so you have n square. If I had a board, I would write on it. You have n square, so the corrections go with n over SBH. So when the page time arrives, this number is order 1, and then you get order 1 corrections to trace rho square. So it's actually, this is exactly, yes, but trace rho in this case you take to be normalized. Yes, yes, yes. So it actually, and the way actually the deviations in this case are quadratic. So they are below the page curve in this case. And this is the typical, this is exactly the strength that is required for unitarizing the yes. So if they were larger, or the multi-particle corrections were larger, then it would purify too fast. And if they were smaller, it would purify too slow. So this is exactly the size that is needed. And we didn't put that in initially, but after you think about it, you see that this is the only scaling that can work.